Good afternoon, everyone, and thank you for attending today's webcast, Airflow and Water Studies in the Built Environment. Our presenter today is Martin Craig. He's the head of Hagerman & Company's simulation team. We're also joined by Mark Lautenbach. He's a solutions engineer with Hagerman & Company. For today's presentation, you're going to be in listening only mode. If you have questions for Martin or Mark, you can, we will provide Martin's contact information at the end of the webinar, and you can email or call him directly. This presentation is being recorded, and you should receive an email within the next day or two with the recording link attached. Also, there will be a survey at the end of the session, and we do ask that you take a few moments to fill this out. And also, this webinar does qualify for one AIA credit, continuing education credit, and if you would like to receive that, you can leave your AIA number in the survey afterwards, and we can submit that for you. And with that, I'm going to hand things over to Martin.
Thanks, Ashley. Hello, everybody, and welcome to today's seminar. As we just mentioned, it's Airflow and Water Studies in the Built Environment, and I'm joined today by Mark Lautenbach. So, looking forward to presenting what we have here. And I thought I would kick off. You know, this acronym CFD stands for computational fluid dynamics, and just the words there can conjure up, you know, complexity, and you know, is it a complicated thing we're getting involved with? Do I need a specialist? Do I need an analyst, etc., etc.? And so I like to break it down into something that's very simple. And what is CFD? And certainly for the you know, industry that we're talking about today, AEC, MEP, and that kind of thing, it's the study of a fluid. And again, in this case, it's air and water and temperature, and as it interacts with surrounding objects. So dynamics is all about movement and motion. Another way of thinking about CFD is color for dummies, and not to be disparaging in any way, using the phrase, you know, sort of analogous to Excel for dummies and things like that. But as we'll see over the next few slides, we're going to see lots of color charts, if you like, and that color, those colors mean something. It's much easier for a layperson, or yeah, you know, we're not simulation experts often in this discipline. So it's one of the things we want to do is present data and results in a way that makes sense to people, such that we can win bids, but we can also understand the nature of the environment and what's going on, and ultimately that allows us to design. And you do design iterations such that we get optimized performance in the products and parts that we're looking for. And later on here, in about 10, 12 minutes, I'm just going to go through a few slides of introduction and setting the scene and giving you some high-level overview as to what we're doing. And then I'll hand over to Mark, and Mark's going to do a live demo of an atrium study. So, you know, what industries though is CFD applicable for? It's the MEP, AEC industry that we're talking about today, but its legacy and history comes from getting involved, you know, solving problems in flow control, electronics, and industrial machinery. But it's all just CFD. It's all just the movement of a fluid and temperature and how it interacts with surrounding objects. Again, just to give you some more of the background, Autodesk CFD is basically a virtual wind tunnel. So this is a very common image that we see in CFD studies, that of a racing car, and looking at the airflow in and around that. So we can look at things like drag. Here we're looking at flow through a cityscape. It's a virtual flow bench, so this is some kind of valve or strainer, and we're looking at the flows. This is really one of the powerful aspects of Autodesk CFD. It lets you do design comparisons. So here I'm looking at 4 different designs qualitatively and quantitatively to assess the performance of different designs compared to each other. It's also a thermal test bench. This is an LED lighting fixture. That LED lights themselves don't create a lot of heat, but the electronics to drive it do. And we're looking at airflow in and around that heat sink, and that was just the inside of an electronics box to show the performance. And the importance of placing vent holes and things like that with regards to airflow. So that kind of just gives you a high-level overview of some of the industries and areas that CFD can be applied to. But bringing it home now, in terms of the audience today, CFD applies to the wastewater industry. We can do wind and wake studies. We can look at pollution control, making sure that emissions from a building don't get entrained back into the building. Or imagine a helicopter on top of this building, and you've got HVAC ducts on the top there. Does the helicopter fumes get entrained into the main airflow? We'll look at clean rooms and healthcare, ventilation and occupancy comfort, and also data centers. And I did notice that a number of the companies that are online today get involved with data centers, and so we'll certainly say a few words about how CFD can be used in data centers. So as I mentioned, I'm just going to go through a few examples here from site planning, emissions control, airports, entertainment venues, hospitals, ventilation systems, parking structures, and data centers. This is a view, sort of a Google Maps view of downtown Manhattan that was then modeled up in something like Revit or maybe Inventor, any 3D product. And then we basically say, wind, go forth and prosper. And here we're tracking the movement of air. And so in any kind of image like this, as I mentioned earlier, sort of CFD is color for dummies, red is high, blue is low. And so we can see where it's red. That just means we have high velocity going around the buildings. And so we're literally following the streams of air. This is important for city planners. They're interested in making sure that you don't get canyoning, that you don't get freak gusts of winds that would create pedestrian discomfort. There was even a case in the north of England in Leeds not long ago where, as a result of building changes in a cityscape, there was a freak gust of wind down an alleyway, and sadly that toppled just at that moment. A double-decker bus was going past. It toppled over as a result of being hit by this wind, and it sadly killed somebody. So city planners are interested in monitoring airflow in cityscapes. San Diego International Airport Terminal is an open front terminal, and the mandate here, before this was actually allowed to be built, but during the architectural stages, they had to do some studies to show that the predominant airflow was going to carry away the emissions from vehicles. And one of the mandates was, if we have, let's say, a couple of shuttle buses here and some cars parked here and up here, would that air get entrained into the building? Would it be carried away? And from doing this consulting study, we were able to show that the design here, because of the difference in pressure on the inside of the building to the outside, was going to make sure that nothing was going to get entrained, and so we weren't interfering with people's comfort there and health. There are some motivators. I just want to interject this here. More and more the demand for green buildings is growing. 55% of architects and 36% of engineers report a higher level of involvement in green projects. There's lots of government regulations that are driving this demand globally, and I'm sure we're all familiar with LEED, and CFD can really speak to two major areas here and contribute to 54 of the 100 points required for the highest level of LEED certification in the area of energy and atmosphere, and also with indoor environmental quality. Continuing the theme of external airflow, and then we'll start looking at some internal airflow as well, but this is sort of a combined one, and this was from Singapore University of Technology and Design. Actually, a Dutch company using our software was involved in looking at or optimizing this building and orientation and layout to capitalize on the natural ventilation effects. And so one of the mandates was it had to have a net zero carbon footprint. So we can see lots of green landscaping around the building. We can see green on the building. And the predominant airflow, maybe the vectors don't come through too well in the go-to meeting here, but the predominant airflow is in this direction. And the consulting firm played around with the shape of these buildings and the orientation of the building with respect to the predominant airflow to make sure that we could maximize the benefit of that airflow and contribute to helping with natural ventilation, and ultimately help contribute to the net zero mandate. Bringing it inside now, the Cincinnati Music Hall. It's a beautiful building, and it's actually a building of national historic significance. The building owner wanted to improve occupancy comfort. Colour for dummies again, red is high, blue is low. So we've got people that are hot up here and people that are cold. And we can see sort of this is called the meshing at the back there. So you can see this has been modelled. We took the Revit model, brought it into CFD. Again, that's what Mark's going to show in a second or two. And we did a pre-analysis, and I'm looking at the pre-analysis here. Subsequent to this, a design change would have been made, the analysis run again, and we would have got a much better distribution of thermal gradients there. So it's really great for retrofitting projects. Obviously, in this case, because it's a building of national historic significance, we couldn't go using trial and error to test different locations of the ventilation system. So CFD is a really great way of playing that what-if game scenario rather than doing trial and error. Looking at that was sort of a retrofit to an existing building, and this was a brand new building, Washington BWI Airport Terminal, and here we have a nice open glass front face. We've got this nice swoop on the ceiling line, so from an architectural standpoint, this looks great. Architects are very interested in the form, but then we have to consider the function as well. And we can see these sort of Titus type inlet vents here. And what the designers were trying to do was utilize, make sure that the air streams came in and washed over the glass, such that the solar loading on that glass wasn't going to create hot spots and during cold weather or inclement weather get condensation. So it's important that it would wash away. We also got this thermal barrier up here, so we don't want to disturb that thermal barrier, and that creates a nice insulating layer. There's no way you could have envisaged the performance of this system without doing CFD. Moving into energy audit and retrofitting of labs and things. So this is a lab at Yale Labs, and there was some concern about the quality of the air in this space for any occupancy. They were dealing with chemicals and things like that. And in this image here, this is the before a design change was made. So this is as the lab was. Red in this case indicates stagnant air, so very, very slow moving air. So if you're a person in this area and you have a bit of a chemical spill, then you're potentially breathing in toxic fumes there. So a design change was made such that we got a much better flow through the system, much more even flow, and it really improved the safety of, not only did it improve the safety, but because we were able to reduce the air changes per hour from 10 to 7, it actually ended up saving over $100,000 per year. And there are numerous types of these labs around at Yale, so ultimately it saved them a lot of money. The report that we got back from the sponsoring manager for this was we could not have proven our point without the simulations provided by Autodesk CFD, upfront CFD, and I'll explain what we mean by upfront CFD in a second. It's not a product, it's more where does CFD fit in the process, but upfront CFD was the only way we could analyze airflow patterns with any degree of confidence without the exorbitant expense of constructing a full-scale model of the space. So I said I'd introduce, or I'd explain what I mean by upfront. And if we consider this triangle representing the global space of anybody and everybody that might want to do some CFD analysis, there are some really good products on the market catered specifically for the simulation experts. These are people that potentially have a PhD, master's level degree, and all they want to do in life is CFD analysis. But what about regular architects, MEP engineers, mere mortal type people who are involved in the design process but are not necessarily PhD propeller head type specialists? And so by integrating upfront early in the process, and by early I mean integrating directly into products like Revit, we can provide a really great tool for architects, MEP engineers, facility managers, to allow them to visualize and optimize their space while still in the early parts of the design phases. These products, of course, have got to be easy to learn because we're not the experts. We're not using these all the time, so they've got to be easy to use and easy to remember how to use, and easy to do design studies. such that we can optimize the products and buildings and spaces that we're involved with. This example that I'm showing you here is actually, I don't know whether you can tell what the image is, lots of squiggly lines. I've had everything from, this is a wiring cabinet and things like that. But again, remember these lines represent airflow stream lines. So we're looking here inside of an operating room. And so we can see the doctors and nurses, we see the hospital bed, and we see equipment in the place. And basically, we're looking at the airflow as it mixes around the whole room. Something like 1 million people get secondary infections every year in the US alone as a result of going into hospital and having some kind of surgery. Sadly, 100,000 people. It costs the healthcare industry something like $33 billion. So a design change was made, and in actual fact, a big plenum was installed in the ceiling, and it created a much more laminar airflow. And here we can see now that the streamlines and the air is not circulating or recirculating. It's being carried nicely away through to the ventilation system. This is an image of a smoke moving through a parking structure. So we can see here the different colors represent different densities of air or different densities of smoke. And the mandate here potentially could have been exit signs have got to stay visible for 10 minutes or a period of time. And so the fire department will be able to mandate that, and then the designers will be able to assess, are we meeting the requirements? And so what I've actually got here is the equivalent of 2 small cars starting, so kind of an 8 kilowatt fire starting, and we're tracking the smoke as it propagates through that structure. I mentioned that I talked a little bit about data centers. The delivery of cooling flows is really important in these mission critical spaces. We want to increase IT density within existing facilities. No sooner has a facility been created, then we're cramming more blade servers in there and things. That just contributes to the increased heat flow and also energy consumption, trying to optimize that. And what we're looking at here, this spinning of a data center, we're looking at above tile and below tile airflow, really fantastic. And we're seeing whether air from the hot aisle, whether it gets entrained into the cold aisle and things like that. We need that separation. Really great way to visualize that. I don't know whether any of us have seen this Apple store in New York City, but it's a pretty large piece of glass, and the architect was really concerned about how they would be able to put in a ventilation system, HVAC system, without it being seen, because that was the mandate. They've never done a project like this where the slot diffusers were not right at the front and above that glass. Normally it's right there above the glass, and it washes down to create the cooling and stop condensation build up and things. But what they actually did, the firm responsible for the design of this from a HVAC standpoint, they ran actually 40 different trials over a very short space of time to come up with an optimized design and flow pattern and distribution pattern of the inlets and outlets to the HVAC system. And on installation, it worked perfectly. No way you could have done that without the use of CFD. And just thinking about, curtain walls and curtains and washing of glass, I just wanted to introduce, although I've said here that the main purpose of today's CFD, computational fluid dynamics, we can also do things like stress analysis on curtain walls. So we can actually take the results from CFD and look at things like take the pressures as a result of a flow, and then bring that into one of our FEA solutions, so we can look at things like structural integrity. So what we're trying to do here, obviously, is assess, and I've tried to sort of intimate this through the examples I've shown you, is to assess performance before it's too late. And typically speaking, from my many meetings with companies in the AEC and MEP world, a typical process, and I've simplified this just for effect to some extent, but it starts with a design concept. We produce hand calcs and energy calcs, handbook specs, and use the history and experience that we've got, and then we go to an install. The problem with this, it's not necessarily the fastest process in the world, and it tends to mean things are over-designed, it's not optimized, it could be somewhat inefficient, and ultimately, though, there's just uncertainty about performance. To illustrate that, we were actually working a few years ago with the Paris Metro. They were extending their line, and they're having to put in a new HVAC system, and unfortunately, on installation, they find it underperformed by 40%. And when we talked to the MEP firm, they said they'd used hand calcs and history, and it had never failed for them before. But unfortunately, they hadn't taken into account something that was in as part of the design. And had they been able to use CFD, or had they chosen to use CFD through that early part of the process, they would have actually found the issue. And so that actually they came to us. We worked as a consulting partner with them, and we came up with a redesign and helped them make sure that they improved the system. The problem was, of course, the MEP firm suffered financial penalties and a loss of reputation, all for the sake of, ultimately, it was a $10,000 investment in software is all they needed to make, but it cost them a lot more money than that in financial penalties, and certainly the loss of reputation is not good. So, that's the process that I just showed. What we really want to do is have the design group implementing upfront simulation. So now we have design groups, whatever your favorite 3D CAD product is, or BIM product, something like Revit. We also use Rhino 3D and things. But you can take that design, you integrate CFD with your design, and then your turnaround is ours, and we're doing local optimization. And now we've got an optimized product, we've got more certainty about the performance, so we can go to install. Just to give you a flavor for some of the companies we've dealt with over the years, and we've been doing this a long time. I'm not sure whether you've heard of Autodesk CFD before, but it's been in the industry for a long time now. So many reputable companies using the software. So we're moving to the demo phase here. Mark's going to take us through sort of a design, looking at an atrium design and showing some results from the first run, then making a design change and getting a different result. The workflow, I really want to stress this, because one of the things I said earlier was this software is easy to use, and I wanted to explain just kind of the workflow. This magic black box, right, the CFD solver handles all the complex stuff for us. If we can create a model, some kind of 3D model, we know the material properties of what that thing is going to be made out of, whether that's glass, whether we're using brick or wood, and we also know the known conditions, things like inlet flow rates and things. Do we have any solar loading on windows? Those are just the 3 pieces of basic information we need. We put those into the solver, and we get the metaphorical answer, number 42, out of it. The 42 means the answer. It's the answer to the ultimate question of what is the meaning of life, the universe, and everything. And then we go back, play some what-if games. Now I've got that answer. I can make a design change, and I get a new answer, and so on. I can start changing my design. Maybe I use different materials. Maybe I look at different orientations, different wind loads, different solar loads for time of the year, and things like that. But this allows me to play what-if games, build up a number of different results, then compare and contrast, and know I've got an optimized model. So at this point, I will hand over to Mark and let him take us through the demo.
All right. Thank you, Martin. First, before I flip over to my screen, I do want to point out it was mentioned that it all does start with a CAD model and geometry and so forth. The image that you see on the screen in front of you, that is from within Revit. So you'll notice that as we build a model inside of Revit, when we want to go over and start working in CFD, it's just a matter of going and hitting this button here, as you see, where it says Launch Active Model. It will take that model and switch us right over into the CFD environment, which at that point you would see something that's going to look something similar to what my screen shows at this point. Okay, so at this point, I've gone from Revit into my CFD, and I'm going to go through and start doing the analysis of that first initial concept that we're building inside of our CAD package. Again, CAD package could be Revit, could be any number of different CAD packages where we're going to build our solids. Excuse me. So at this point, You know, it is just a matter of going through those 5 different main areas, and you'll kind of see it both across the top of my toolbar here, where we've got our materials or boundary conditions, and then eventually we solve it. But it's also in our tree on this side here. You'll see material section, boundary conditions, mesh sizing, and so forth. Well, how does that all work? It's all about how do we want to define information. So when it comes to any of the parts in here, you know, I'm just going to go in and I can say, hey, let's make this some sort of material. So give it some of the properties of what is it, you know, whether it's glass, whether it's concrete, whether it's steel. You know, there's all sorts of different materials that we can apply, whether they're solid materials. We could go in and put in things like fans that are going to then turn around and help push the air and move the air, or some blowers, you know, if we were getting into other rotating types of items. Again, LED devices, you know, we were talking about the lighting and so forth. So we've got all sorts of different types of materials that we can assign to parts, and then from there we've got a bunch of different excuse me, this button is what I'm looking for, all the different materials that we can use. Again, whether we're talking concretes, as you see, different types of flooring, glass, carbon, you know, so we've got a bunch of different things that we're going to assign to our parts. And we go through part by part in essence, and you'll see I've got this nice little tree that's kind of defining and telling me that, hey, you know, everything has been assigned to some sort of a material. Okay, and that's kind of really a big key, because if it doesn't have a material, CFD is not going to know what to do with it. It's not going to understand and how flow is happening. Well, is it a particular material that's going to be able to flow, or is it not? Okay, so we go through and we assign our materials. And a couple of interesting, nice little things I want to point out. This is an office space. Okay, it's a lobby to a facility. Well, if I turn off the visibility here and I hide my windows, right, you'll notice that I can't really see inside. Well, one unique thing that CFD will do for you is it will build a volume, okay, of your empty space, of the void inside of your environment, especially in the case of, say, a room like this, of a building. You know, you've got that void where the air sits. Well, instead of you having to deal with building it yourself, CFD will see that void and say, hey, this becomes a volume. And you'll notice as I hover here, I've got it configured to be that is our moist air. So if I turn off the visibility here, just so you can see inside, okay, now I'm looking at the rest of the facility. You know, I've got our concrete floor, I've got our different walls, okay, there's a hardwood railing here around the mezzanine, you know, and then of course we've got our couches, tables, stairs, and most importantly we've got a couple humans in here because, hey, you know, we want to know what is their comfort level going to be both up in the mezzanine and down at the lower ground level, right? So in essence what we're trying to find out with this particular setup is, you know, we've got these diffusers where the airflow is coming into the space. Is that air going to make it down and keep everything circulated well enough, or do we need to make a change, right? So we go through and we define all of our materials. Second step in the process is we tell it the boundary conditions. Really, the boundary conditions are just what's happening in your environment, right? How much airflow is moving through the different areas, okay? So you'll see we've got a series of things that we set up here, okay? We go through, and I'm going to flip around the back side, okay? Here's all of our ducting. And you see I've got some color stripes on this surface. Well, these color stripes are telling me that, you know, the air as it passes through at this particular point is at a specific temperature. So we've got 90 degrees Fahrenheit. We've got a specific amount of humidity. And you'll notice that in this case I've got a thing called a zero pressure gauge. Just mainly saying that at this point it's freely flowing both directions, or whatever direction we're moving at. And then there's another place in our model where I've got a volume flow rate. Okay, so that volume flow rate is just telling me in this case, you'll see, let me expand this tree a little bit, and you'll see that I've got a volume flow rate of, in this case, 142 cubic feet per minute going through this particular setup. Okay, so just like we did with our materials, all you're doing is picking on a surface and saying, okay, what's happening here? Are we dealing with our pressures? Are we talking about the flow rates? Again, temperatures, if we want to take temperature into consideration here. Humidity, what's the humidity of that particular airflow at that point in time? Okay, so we'll go through and set up those conditions for this particular analysis. The next thing that needs to happen really is what we call meshing. Okay, and meshing, what it is it's how any of these analysis packages go through and do its computations. Okay, so it has to break apart all of our parts, all of the surfaces into more manageable chunks. Well, the way that this does it, it's kind of unique because, the mesh can be a challenge sometimes, and that's always the, anybody that's talked about doing some analysis, they say, oh, meshing is so hard, and it's really, the difficult part of doing all this. We've got this auto-sizing function where CFD will break apart everything kind of automatically, and for the most part, it, in my experiences, I can just about use auto-size and not have to think about going back and doing things. You'll notice these dots. It does have all sorts of different amount of dots in different areas because the software looks at two main things to determine how it wants to do it. It looks at edge length and curvature. And as the lengths of the edges get smaller or as our curves get tighter, it knows that, hey, on smaller places, I need to have more, break it up more. So as you look in here, the different edges of the different parts have a tighter amount of dots, okay? And the dots are just the representative of where and how is it going to break it apart. So it does this fantastic job to really analyze the model itself without you having to go back and interact with things. Now, of course, if I want to really kind of fine-tune and look at different areas, I can go in and I can make all sorts of changes and make it as tight as I want or as coarse as I want. But just on its own, it does one fantastic job to determine how much do I need to break it apart and how much do I not need to break it apart. So at that point, we've got ourselves all set up, and all I need to do is hit solve at this stage of the game. And when I go to solve it, it's going to go through and it's going to start slicing this apart and determining what's going on from the point that I say go until it says that, oh, I know exactly how much flow is going through this system, and I have a good understanding of what's going on. So let's go ahead and just kind of start taking a look at what's happened. Okay, and let me squeeze this back down so that I have more space to look at actually what's happening. So here we've run our results, and yeah, it's again, as was said, colors for dummies. So in this case, I'm looking at velocity of airflow. Well, blues are nice and slow, as you see. A blue, according to my chart here, is going to be zero flow, and then as we get up into the reds, it's a higher rate of flow. So you see up here I've got some higher rate of flow, but I'm just looking at the outside. It doesn't really tell me much about what's truly happening inside my model. So I'm going to go ahead, I'm going to slice it apart. Okay, I'm going to put in this slice plane so that I see what's really happening inside this environment. And this plane, again, I'm just looking at velocities, but I can go in and I can take it and I can just kind of drag it, move it around. And you see as I get to where that inlet's at, well, yeah, I've got a whole huge amount of airflow just shooting straight down to the floor. And as it gets down to the floor, it slows up, and then it splits off to the sides, and it gets even slower. And it doesn't look like there's a whole lot going on in most of the area here. Well, you can take this, and I can twist it around and look at different areas in different directions. So here you see there's another inlet coming over on that side. You know, and again, I can just start moving this and seeing how things are moving, and you know, again, it's kind of showing me, you know, what's happening. Well, that's just all in just basic colors. Well, maybe I want to take a look at it slightly different. Instead of it being colored, let's throw on actual vectors on here. Okay, let's take a look at some arrows on that plane. Okay, maybe I'll make them a little bit smaller, but I'm going to add more of them to the plane. Okay, so we can really start to see, you know, and if I zoom in on it, you can see that, yeah, it's pushing straight down up here. I probably have too many. Okay, it's pushing straight down, and then eventually it's flipping and it's turning. And if I look at it from a side angle, you can even see, you know, if it's coming away from those planes and which direction it's going. So, you know, we can kind of start seeing, getting a little bit more information about what's really happening here. Now that's, you know, again, with any plane we can do that. I can change the orientation. Let me switch this back just so that, you know, sometimes it's a little bit easier to see some of these changes as I do it with a solid plane. Instead of it being cut in one direction, I can cut it, you know, in that direction, or really maybe I want to look in this plane. Okay, so we can change it in any planes we want to. And again, and see how things are moving. Another method we can do, instead of looking at it planes, is I can use what are called isosurfaces. An isosurface is just where I can go in, and in this case, I'm still looking at it in velocity, but I can see where is the surface of air moving at a specific rate of speed in this case. Okay, so, you know, here I'm looking at 71, but if I move it a little bit to where it's quite a bit slower, you see a much slower moving airflow is all in this area. If I don't want to talk airflow, I could be talking temperature, right? So I can quantify it based upon temperature, and I can also then color it based upon temperature. So if I want to see it at a higher temperature, you know, we get it in different areas. You know, it's high on the outsides, whereas when we get towards the middle of the environment, you know, it's cooler down in that range. Okay, so you can start looking at things in that realm as well. Okay, so we've got different surface boundaries, shall we call it. Now, another thing I can do, let me go back to a plane for a minute here. You know, maybe, let me rotate it a little bit. And then, just like with the isosurface, I can go and look at temperatures. Okay, and not only can I just look at temperatures here, but I can do a plot of points of information. Okay, and I can just start saying, well, you know, what's, you know, grab a couple different points, okay, from one to another, and hit a plot line, and you can see as we go from point A to point B, you know, what is the temperature change happening. Okay, so at either end, you know, the temperatures are, right, isn't that, yeah, that's what I'm looking at, is temperatures. It's cooler air here, but then in the middle it's warmer, right? You know, so I can look at temperature change through a specific line segment if I wanted to, and have a bunch of different points. You see, I could have done more points just depending upon how I was going. Okay. So I can start graphing some of that information and have actual quantitative data that I can actually read numbers off of. And then one last little thing, let's say I flip it over here. What is that? Let's go back to this Z level. Oops. If I bring it up into this realm, I use this just so that I can kind of see where that airflow is really coming in at. Well, I can now go in and I can create a set of points. Okay, I can do these traces where these traces will allow me to go in and say, you know, where is the airflow actually moving from those points? Okay, so I can see that it's coming down and it's flying around, and yeah, I can even go in and animate it so I can see, you know, the actual process. Pause that and rewind. It's going pretty fast. Okay, but you can go through and we'll be able to see, you know, really what's happening with where the airflow is going. Okay, and you can even take snapshots of this. Okay, you'll see I've got summary images and static images. I can save out animations of this whole thing. Okay, so we can kind of get some better details about this. Well, that's fine and dandy, but now, you know, I need to make a change. Maybe I want to take a look and see, well, what if I use a different flow rate? Or what if I change the actual inlets, right? Or how the airflow is moving in. Well, instead of having to redo a bunch of stuff, I can go in and I can clone different things. Okay, I can clone my this setup here, and when I clone the setup, it will copy everything over to a secondary setup where I can then go in and define different conditions. Okay, because remember, we've got those different steps. We've got our design that we might want to have to manipulate. We might want to look at different operating conditions. So in this case, I've got a different flow rate. Okay, I would go through and do, all I'd have to do is once I cloned it, change my flow rate, resolve it, right? Maybe I want to go in and do a completely different configuration. Maybe the inlets, you know, where the ductwork and where the airflow is coming in, maybe I want to throw in different types of diverters. So instead of it just shooting straight down, I want to throw in some sort of a diverter. So I would go in and I would clone my entire design. Again, when I clone my entire design, what it does is it copies everything that I've done previously. Okay. You know, so these two different setups, as far as the two different flow rates, it's going to copy all of that stuff over. And then I would go back to my Revit model, make my change to the geometry in the Revit model. I would then say, okay, let's take those changes and push that into this design here so that I can then go in and rerun it and reanalyze things, right? Now, instead of me having to go in and look at each one of these and go through all those same steps that I did with the planes and the isosurfaces and the traces and so forth, what happens is, as I do it that very first time, it's saving that information so that I can use this thing called Decision Center. And when I'm using this thing, Decision Center, it's allowing me to look at, okay, you know, here is all four of those designs. And I can go through and take a look. Okay, this was the first rates, okay, with one flow rate shooting straight down, and then if I had a higher flow rate, well, this is what it looked like. And then I went to my secondary design, which you see has a diverter at the top, so the flow is changing, right? And I can take a look and see which one is working better, whether we're talking about this draft rating, or maybe I want to look at the actual people inside there, okay, and I want to see, you know, how are their comfort levels as far as what their temperature's like on the different surfaces based upon how those flows are going from one to another. Okay, so I can start looking at it both in an individual state like this. As you see, I'm going one by one. I can split my view. Oops, that's not the one I wanted. I want to go over here. I want to make two viewports. That's what I want to do. So in this screen, I can be looking at one view, and on this one, I'm looking at a different one. So here you see I'm looking at design 1 at this setup. This one I'm looking at design 2 in a secondary setup. And they're all linked. So as I rotate and change the position on one, it keeps me looking at the same information in both locations. So I can start going through and really seeing a side-by-side analysis of, hey, you know, as I go through and make the change to my geometry, is it making it better or worse for the individuals in this environment? Okay, so, you know, you can see color-wise the two individuals are looking at things, are feeling things different. Okay, and you can kind of determine, okay, well, you know, maybe I want to look at humidity. You know, how's the humidity passing as we go from one to another? Or, you know, how does the person feel? And then same thing with that quantitative data. Okay, I can start looking at, okay, here's my 4 different configurations, you know, based upon the data that I need. You know, we've got all of our results right here to give a good determination of, hey, which setup, which configuration is really going to work best for us. And with that, I'm going to pass it back to Martin.
Fantastic, Mark. Thank you. Thank you. We'll just grab the screen. Great. So I hope you were able to see there what Mark did is I just go back to the workflow. He described he was taking a Revit model. He's bringing the Revit model into the solver. He then told the system what the materials were, the components. He defined things like flow rates, so the known operating conditions, and then he solved and he got an answer. And then Mark went back and said, I'm going to clone the first setup, and he created a second scenario. He then described how he would have made a design change, and that is pushed back in then to that second scenario. And what we ended up looking at was 4 different designs in the decision center, and the decision center is all about deciding which of the different designs is the best one. So that's the real power of the CFD workflow, is that very, very quickly you can get to multiple different designs or results of different designs, so you can compare and contrast. In the spirit of transparency, just so you know what we're talking about here from a pricing standpoint, the software costs just over $9,000. There are 3 different tier levels, if you like, but 99% of everybody in the AEC, MEP industry uses the CFD advanced product, and that is $9,200. Some of the benefits of simulation in AEC, we can visualize that before we build anything. It helps us create innovation. That's a key point. When you start playing around with this kind of software, it just lets you get creative, and you can test what I like to call crazy ideas and see if those crazy ideas might help bring about an improvement. And if they don't, if it's detrimental to the performance, then let's get rid of it right now. But at least it allows us to be creative and innovative. We can assess potential liability issues, faster project completion. We can optimize the airflow for comfort and safety. We can take the results from the CFD analysis and show that to a customer. Again, working on this principle of color for dummies. And we've had no end of stories back from our clients who say we've used the software and it's actually helped us be more competitive, and it's actually helped us show credibility and earn credibility with our customers because they can see we're doing CFD analysis. And ultimately it helps us save money on the products or designs that we're creating. However, we recognize that for everybody, CFD may not necessarily be required. Maybe you're only doing projects once every 3 years. You know, whatever the time period is, and you've got to assess your own return on investment for this. And maybe you don't have access to people that could use this software. Maybe you don't have the bandwidth, whatever the reason is. So Hagerman has a full services consulting team. And so if this is an area that sort of intrigues you or interests you, let me know. Maybe the software is the right way for you to go, and we'll certainly work with you in the spirit of partnership to help determine whether that's the case. But if in the end we determine it's not, it may be better for you to consider our full services consulting. And so that about wraps it up today. I appreciate everybody's time. Again, as Ashley mentioned, feel free to reach out to myself if you've got any technical questions or commercial questions. I'll certainly do my best to answer them promptly, and certainly we'll pull in Mark for anything that's overly technical from my point of view. But Martin Craig at hagerman.com, and with that I'll hand back to Ashley. Thank you.
Thank you, Martin and Mark, for the great presentation. I don't really have anything else to add other than to say thank you for attending the webcast today, and have a great day, everyone.